All right, did you guys prepare yourselves for insanity? All right, I got to change this color. I hate the red stuff. All right, so let's make another function. Only let's make this one a little more interesting. Something like this, okay? So if I've got, this is f of x, and I'm going to go from A all the way out here to B, okay? But I'm going to, excuse me, maybe I look at this thing and I'm like, wait, this function's got all kinds of weird behavior. You know what I mean? So some of my approximations are going to be under and some of my approximations are going to be over as I go through this. Is there a more clever way? All right? And there is. It's something called Simpson's rule. Now, within the scope of this class, it's very difficult to prove Simpson's rule. It's kind of a pain in the butt to prove it. And to be honest with you, it's such a funky rule that we don't really worry about it so much. We're going to worry about the rule, but we're not going to worry about where it comes from so much. But watch. Here's what Simpson said. He said this. He said, let's bust this thing up. And since we're pretty good at taking integrals of polynomials, then let's think about this thing as being just a bunch of quadratics. So if I had a quadratic that looked like this, and this was before people know how to take definite integrals, they could figure out the area underneath a quadratic. They could do it geometrically. So they said, all right, I can figure out the area under this guy. Now let's come up with another quadratic. Instead of one opening downward like this guy did, let's do one that opens up. And then I'll figure out the area under this guy. You see what I'm doing here? And then let's grab another one, because this one's kind of quadratic, right? Comes up like this, and we'll figure out the area under that one. And then last but not least, we'll figure out, ooh, purple, I haven't used that one. We'll figure out the area under this guy, because that seems to be a lot more accurate, right? Because it takes care of the curvature of the function, whereas these clunky rectangles and trapezoids either over-approximate or under-approximate, and they rely a lot on luck as far as being able to be accurate. Like remember with the midpoint, because of the fact that it over-approximates on one side and it under-approximates on the other, typically, but not always, it relies a lot on luck, whereas this picks these curves up pretty nicely, doesn't it? Now, there's a formula for it. And I'm just going to give you the formula. Again, I don't want to bore you with unnecessary proofs. And this is one of those that I deem to be unnecessary until you get into the more fun analysis courses. Then you'll prove it, and it'll be worth it. But for those of you that aren't going to go on to your analysis courses, we're not going to force you through it. Okay, you ready? So if I want to take the integral from a to b of f of x dx, this is going to be approximately equal to, you ready? S sub n. This guy means Simpsons. Simpsons with n approximations, so n of these little areas right here. The formula is real simple. It's just delta x, just like always, because we want these all to have the same width. All right, delta x, remember delta x is always b minus a over n. All right, so I got delta x over 3 this time. Again, don't worry so much about where these come from, but watch how this works. I'm going to take f of x sub 0. It starts a lot like the trapezoidal, and then that's pretty much where it leaves. Watch how this works. We go 4 times f of x sub 1 plus 2 times f of x sub 2 plus 4 times f of x sub 3, right? Plus 2 times f of x sub 4. Now watch, this notation gets a little bit ugly, so bear with me. Plus, dot, 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 and then we're going to go plus. And the way it works is it goes 1, 4, 2, 4, 2, 4, 2, 4, 2. And then what we have to have is we got to end the way that we started. So it's going to be 2 times f of x sub n minus 2 plus 4 times f of x sub n minus 1, and then plus f of x sub n. So think about it this way. It goes 1, 4, 2, 4, 2, 4, dot, 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 2, 4, 1. Which implies to be able to use Simpsons, if you think about it, because we always pick up the end point. So if I've got, excuse me, if I've got n sub it or 8 subintervals, then I'm actually going to have 9 values, right? So I have to start at a 1 and I have to finish at a 1. So what that implies is that n must be even. Must be even. And you can sort of work, must be even. And you sort of work through why that is. If it's odd, it won't work. Like let's say that n equals 7. Well, watch what happens. You get a 1, 4, 2, 4. Now remember, see what's happening? This is my end guy right here. 2, 4, 2, 4. Why did I pick 7? What a ding-dong. 2, 1, 2, 3, 4, 5, 6, 7, and there's that. See, I don't get that symmetry. See, it's got to end in a 4. It's got to end in a 4. Well, it's got to end in a 1, but the number right next to the 4, or the number right next to the 1's got to be a 4, both in the beginning and in the end. So n's got to be even. Well, that's no big deal, right? You just pick an even one. All right? All right, now what we want to talk about is something called error bounds. These are great. And to be honest with you, we don't even have to talk about these in the context of AP exams or really even the CVEs, but it's a wonderful introduction to the error bounds that we are going to have to deal with on those exams and in this class. So it's a really cool way to explore error bounds. Here's what I want to be able to figure out. An error bound simply tells me how far away can I expect the approximation to be from the real value, Now this is really important. I want you to understand this. The real value, even if I can't know the real value. Let me give you an example. Okay. For example, if I want to find the integral from, say, 0 to 5 of e to the x squared dx, there is no analytical way that I can know this. I can't know it. I know what e to the x squared looks like. E to the x squared looks like this crazy parabola. All right, this guy right here is e to the x squared. The problem is there are no tricks out there. There's no substitution, there's no parts, there's no trig subs, there's no clearly partial fractions. I'm screwed. I cannot figure out analytically how to take the antiderivative of e to the x squared. So I can't know the real value. However, I can use all sorts of these approximation methods, right? I can use the m sub n, I can use the t sub n, I can use the s sub n. I can also use L sub n and R sub n, but I think we already determined that n sub n pretty much precludes either of these guys, right? It's going to be, why use these guys if I know that n sub n is going to be the best? Now, I'm going to show you something, and I don't want you to panic because it's going to look really, really crazy at first. All right, this is called the error bound, and we're going to do this for the trapezoidal rule. We're going to do it for all three. I will tell you right now that I have a very difficult time remembering these. So if I can't remember them, I'm not going to expect you to have to remember them all the time. All right, I may tell you which ones to remember for an exam, but I'm not going to tell you, all right, you got to remember this, and you got to learn it like vocab terms like we have with some of our derivatives. Now, let's write this thing down. For the trapezoidal approximation, the error, this E sub t means the error that we can expect is going to be less than or equal to, now let's not worry about this k for just a sec. This is going to be b minus a cubed over 12n squared. Now, let's look at this real close. Let's just deal with this function. So right here, avert your gaze over to this side. All right, so I've got a function. I know what a and b are. They're the beginning and the ending of the interval that I want to find the area, right? So that's easy. I know what n is. I get to pick n, right? If it's t sub 10, then n is 10. If it's t sub 5, then n is 5. But what is this crazy k thing? All right, now let me show you what this means. What k is, k is a value where k is always greater than the absolute value of the second derivative of x. Again, I'll say this a lot, especially in this section. This is beyond the scope of our class to be able to prove. We're just going to play with it, okay? So really, all that we have to do is we have to find a number, any number, that we know is going to be greater than or equal to the second derivative of the function on the closed interval from a to b. I'll show you what I mean by that here in just a sec. Okay? All right, so don't panic. Now, let me give you this other formula. We'll do it for all of the formulas. I like to give them all at once. I'm going to give you for the error for the midpoint. Now, why do we put it in absolute values? Well, error is always positive. It's like a distance. Okay? And it's almost exactly the same formula. I get a k times b minus a cubed, again, all over 24n squared. Now, look real close. Again, k is exactly the same thing. So where k is greater than or equal to the second derivative, the absolute value, on the closed interval from a to b. All right, sorry, I'm screaming into the microphone. Guys, look at these error bounds right here. Look at the two. Which is more accurate? This guy, the midpoint, or the trapezoidal? Straight off the bat. And how can you tell? Well, they are identical equations, except for the midpoint, let me change my color, has a 24 in the denominator. And the error bound for the trapezoidal has a 12 in the denominator. Which is more accurate? Well, if I've got a 24 in a denominator, it means that the fraction itself is going to be smaller, which implies that the error is going to be smaller. So just as we suspected from our previous adventures, this guy's more accurate than the trapezoidal. Now let's do Simpsons. You ready? Let's do the error bound for Simpsons. So let me change my pen real quick here. Now, Simpsons is not as pretty as far as its error bound. Excuse me. The error bound for Simpsons, we do E sub s, is the absolute value of. Now, same sort of deal. We've got k times b minus a, only this time it's to the fifth rather than cubed. And in the denominator, we get 180 n to the fourth. Now, look at that. That's comparatively speaking, which do you think is the most obvious? Well, intuitively speaking, which do you think is the most obvious? If I have the ability to make curves to approximate a curve, then chances are it's going to be more accurate. Well, you can tell by the denominator. Since n is always greater than 1, right? I mean, I guess it could be equal to 1, but it would be a decidedly boring problem. Since n is always greater than 1, look what's going to happen. Check it out. I'm going to end up with 180 in the denominator, n to the fourth rather than n squared. Now you may say, but Ripley, what about this b minus a to the fifth? Well, this guy's still going to win most of the time. Most of the time. I guess it'd be an interesting proof to see if it happened all the time. Ooh, let me show you one other thing real quick. There's a difference here. In this case, the k, rather than being being greater than or equal to the second derivative, k is always greater than or equal to the absolute value of the fourth derivative of x on the closed interval from a to b. So really all that we're trying to do is we're trying to figure out a number that's greater than or equal to all of the values of the fourth derivative of f. Now let's go ahead and try one of these. Let's play with it, and because I know it's really intimidating with all these crazy formulas, right? And then I'll do some error bounds with you, and then in class we'll do some more. Okay, but let me do one for you right now.